Well, there was a question waiting for you on the Socrative app here today, and if you're having a little trouble getting started with this one, let me go ahead and zoom in on this a bit. Because if you're saying, well, we haven't covered this yet, well, yeah, you're right, we haven't covered it directly yet, but we did finish with the example on Thursday where what we were doing is we were looking at the automobile example. And where is that? Here we go. We're looking at something like this, and when we looked at this particular example, we were talking about these numbers out front being coefficients in a balanced chemical equation, very similar to what we are seeing, I guess, right here on this equation, where these coefficients now are going to represent numbers of moles. Now, they could just as well represent numbers of molecules. For example, these are all molecular compounds. So we could say that 2 molecules of, what is that, hydrazine, 2 molecules of hydrazine react with 1 molecule of dinitrogen tetroxide, yielding 3 molecules of nitrogen and 4 molecules of water. And we call that the molecular interpretation of that chemical equation. However, for the types of calculations we'll be doing here in chapters 3 and 4, it's going to be helpful if we think of these coefficients in terms of moles. In other words, if we take and multiply each one of them by Avogadro's number, and then consider it to be 2 moles reacting with 1 mole, producing 3 moles and 4 moles. So based on that then, you should be able to go back and say, well, now if we have 63.9 moles of N2, how many moles of N2H4 can we make? And so of the 9 people that answered, let's see how they did. It looks like they correctly, most of them came up with 42.6 as the result. So, to show how we might go about doing that, in case you're getting a little slower start on this, this now is actually the first question on your handout in the packet. If you came in late, and we ever do have handouts, you'll always find them right up here on the front bench. So if you came in late, you'll find it right up here. And this reads now 63.9 moles of N2. We're trying to make, or we're trying to figure out how many moles of the N2H4. And we then need a relationship between moles of N2 and moles of N2H4. So what we do then is we look at the coefficients in the balanced chemical equation, and what do we put in the bottom of this equation for this calculation? 3 moles of N2, and on the top we put in 2 moles of N2H4. In other words, what we did is we compared this value and this value right here. Just like when we were doing the example in class on Tuesday, if we wanted a relationship between cars and bumpers, we said that for every 1 car we have 2 bumpers. So back here, for every 3 moles of N2, we have 2 moles of the N2H4, and that's where these numbers come from. These numbers here come from the coefficients in that balanced chemical equation. And those of you that recall this from your previous experience in chemistry, what do we call this conversion right here? Anybody have that?
Ratio.
What type of ratio? It's called a molar ratio. It's called a molar ratio. And in the molar ratio, the coefficients come from the coefficients in the balanced chemical equation. And again, this is no different than what we did in here on Tuesday, where in effect what these were molar ratios. Because again, we look at the coefficients. If we wanted to relate wheels to cars, we said that there's 4 wheels for every one car. And this here is that ratio between them. And so here in the equation, we use those coefficients in the chemical equation. So then we multiply this through. We take 63.9, multiply it by 2, divide that by 3, and we should wind up with an answer of 42.6 moles of the N2H4. So any questions on this one here? All right, then we go on to the next question that's in your packet there. And now this next question is going to be more like reality. And this one's more like reality because in the lab we don't measure moles, we measure stuff in grams or in milliliters and stuff like that. So we don't have a way to count out atoms directly. So the way that we wind up counting out atoms is based on the number of grams or its mass that it has. So now when you encounter this one here, looks like we are given a mass and we are looking for a mass. So in other words, we are given the mass of this stuff and we're trying to find the mass of this stuff right here. So with this one now, oh, and then the other thing, here's another thing that trips people up. Sometimes it's the wording, and this wording bothers some people. It says that it's reacting with an excess, and that probably should have said reacts with if I was correct in English. That reacts with an excess of N2O4. I'd like to know what mass of N2 is produced. Take you back to the example with our cars once again that we did on Tuesday. And let's say that the question from Tuesday was worded just a little bit differently. And listen carefully now. This is our equation. Let's say we'd like to know how many cars we could make if we had 60 bumpers and an excess of frames and wheels. How many bumpers could we, or how many cars could we make if we had 60 bumpers and an excess of frames and wheels? It'd be 30, right? Because if we have 60 bumpers and there's 2 bumpers for every 1 car, we'd then take the 60, multiply it by 1 car over 2 bumpers, and we'd wind up with 30 cars at the end. And the fact that we had an excess amount of frames wouldn't matter. It just means that we have plenty of frames to use up. And the fact that we had an excess of wheels doesn't matter. It just means we have more than enough wheels to use up all of the bumpers. So when you read these problems, don't let this word excess scare you off. It just means it's telling you, don't worry about N2O4. We have so much of it, it doesn't matter how much there is. So basically it's telling you to ignore it. So with that in mind then, we go ahead and start this problem. And we have 327 milligrams of the N2H4. Now I'm going to make a really quick change here. I'm going to leave the milligrams in for right now, but in the problem, instead of calculating this in terms of milligrams, I'm going to calculate it in terms of grams. So just bear with me here. We're going to take this all the way through with grams, and I'll show you why here at the end. And then for the mass, for right now, let's calculate this answer in grams of N2, and then we're going to convert it to milligrams of N2. And again, we'll talk about why in just a bit. So if this had been worded, again, we're not changing the wording unless you want to think of it temporarily. We're thinking of it temporarily as being 327 grams. So now, if we want to use this chemical equation, the first step we're going to have to do is to take the number of grams of N2H4 and convert it to which stuff? Which units? Okay, first of all, what do these coefficients stand for in here?
Moles.
Moles. So they don't stand for grams. That means our first step is going to be to convert grams over to moles. So let's convert grams of N2H4 over to moles of N2H4. So now hopefully we can do this without writing out all of the conversions. I'm going to put grams of N2H4 on the bottom, and I'm going to put moles of N2H4 up above. Now to convert from grams to moles, how do we figure out the relationship between grams and moles here? What do we need to calculate? The molar mass. That's right, we need the molar mass. So the molar mass is always the grams contained in 1 mole. So again, we want the grams contained in 1 mole. So we go back to our periodic table. If we don't have our periodic table handy, let's get it out. N2H4. We have 2 hydrogens, or 2 nitrogens, and 4 hydrogens. So we're going to have 28.02 added to 4.032.
32.052.
All right, so let's just go with 32.05. 32.05. So we put in the 32.05 right here. And I'm trying to leave enough space here, so we'll have the 32.05. I'm going to put in grams of N2H4. I'm going to leave a little space here. This is 1 mole of N2H4. Well, now we have moles of N2H4, which isn't the same as N2, so we need to convert from one substance to another. And how do we convert from one substance to another? Use the molar ratio. So the molar ratio then is going to be one that relates these two right here. So we want to relate moles of N2H4 to moles of N2. 3 over 2. Okay. 3 moles of which stuff?
N2.
3 moles of N2 on the top and
2 moles of N2H4.
2 moles of N2H4 on the bottom. Again, this comes from relating the coefficients in this chemical equation. And at this point, these units here cancel out. So now we have moles of N2. We're trying to get over to grams of N2.
Put mole on the bottom.
Put mole on the bottom, exactly. And what are we going to put on the top?
The molar mass.
The molar mass, right. So we put the 1 mole of N2 on the bottom, and on the top we're going to put the molar mass. Now we should be able to do this one in our heads. The molar mass of N2 is going to be 28.02. That's because we have 2 nitrogens, each at 14.01. So now, if we were to cancel out these units, we would wind up with an answer in units of grams. Now, remember though, that in this problem, we weren't given the grams, we were given this measurement in units of milligrams. And the prefix milli means 1/1000th. Now it turns out that if we would multiply everything here in this equation by 1/1000th, that means that'd be the same thing as changing this to units of milligrams. This would be milligrams per millimole. This is millimoles per millimole. And this then would be grams per millimole. So basically what we're doing is we're simply adding in the prefix milli in each one of these. And we can do that because really all we've done here now is we are reflecting what the actual units are here. And if we put in 1/1000th over 1/1000th, 1/1000th over 1/1000th is equal to 1. This is equal to 1. This is equal to 1. So we're just basically multiplying by 1 in all cases, but we're using the units that are already in there. So what we're really saying here then is that 1 millimole is the same as 32.05 milligrams of the N2H4. And it's one of those tricks you should think about using, because if you had started this one with 327 milligrams and then convert and say 1 gram for every 1,000 grams, you're adding on more steps, because at the end you would have to go back and convert your 1,000 milligrams for every 1 gram here at the very end. So by simply putting in those prefixes, you're skipping some additional steps that would just take up more space and more time here in your calculations. So now if you carry this all the way through, you could now go through and solve this. We'll take 327, we'll multiply it by 3, and again by 28.02. We'll divide it by 32.05, and divide it again by 2. And we wind up with, now how many sig figs should we have? I hear 3, I hear 4.
3.
There should be 3. So we put in 429 grams of N2. And that's not grams, it's going to be milligrams. Milligrams is what the answer is going to be in. Milligrams. Okay, any questions on this one? All right, looks like we have another one in the packet here. Next one down reads, how many molecules of N2O4 are required to make 36.0 grams of H2O? So this one, once again, we start off with what we're given. We're given 36.0 grams of H2O. We are looking for what in the answer? Molecules of N2O4 is where we're headed. So again, we are given units of grams of H2O. We're trying to wind up with molecules of N2O4. So since we have two different substances and they're related to each other using this chemical equation, it's always helpful to go ahead and identify where they are in the equation. If we're going to use this equation, what does this first step have to be? Convert it to moles. So we need to convert the 36.0 grams of H2O over to moles. So to convert the 36.0 grams of H2O over to moles, what do we put in the bottom? Grams of H2O. What do we put on the top? 1 mole of H2O. How many grams do we want to put in down here? Avogadro's number? What goes in here? 18.02, that's right. We want the molar mass, which we get by adding together the atomic weights. So we have 18.02 grams for every 1 mole. Now that we have this in moles of H2O, we can then convert to the other substance, which is N2O4. So how do we convert from one to the other? That conversion is called molar ratio. So we come back here, do a molar ratio. On the bottom we'd put in how many moles of H2O? 4. And on the top we'd put in 1 mole of N2O4. At this point, moles of H2O cancel out. Then we have one more step. We have moles of N2O4. We'd like to get over to molecules of N2O4. So you may remember on Tuesday we looked at a series of conversions. We said 1 mole of N2O4 is a certain number of grams of N2O4. It's probably not going to be relevant in this case, but what will be relevant is that there are 6.022 times 10 to the 23rd molecules of N2O4. And of course, if we wanted to add this together, we can. Whatever it is, 28 and 64 is 92. I think. You can verify, but again, it's not relevant in this one. What's going to be relevant is this relationship right here. So when we use this relationship, what are we going to put on the bottom?
1 mole of
1 mole of
N2O4.
N2O4, and on the top, Avogadro's number. So this would be molecules of N2O4. We can then go through and calculate this out. Remember how to do these now on your calculator using your EE button or your EXP button. We'll take 36, divide this by 18.02, divide it again by 4, and then multiply by Avogadro's number. How many significant figures should be in the answer? 3. So this should be rounded off to 3.01 times 10 to the 23rd molecules of N2O4. Any questions that you have on this particular problem? Okay, next up. Next up, we're going to take a look back to limiting reactants. We'll go back to where we were in our previous class and think back to the problem here. The problem was something like this. We said that if we have one frame reacting with 2 bumpers and 4 wheels, we make 1 car. And then we were given 50 frames, 80 bumpers, and 100 wheels. And the question was, how many cars could we make? And so we came up with an answer of 25 cars. And why was it we did not keep either of these answers?
Don't have enough wheels.
Don't have enough wheels, exactly. We run out of wheels, so once we get up to 25 cars, we can't make any more. So what we basically do is that even though we calculate these numbers out here, these here aren't the answer. We basically wind up selecting the smallest value, and we call that the theoretical yield. And then we said that the 100 wheels was the limiting reactant because the limiting reactant limits the amount of product that could be produced. So what I'm going to do here next is I have another handout, and this one now we're going to do as groups. And we'll need 3, or I guess since there's maybe 4 in a row, I wouldn't be opposed to 4 in a row here. Just divide this up so nice and easy here. So maybe if we just go 2 tables, the 2 tables side by side, you're working together as a group. And so there's only room here for 3 names, but you can put a 4th name on there if you wish. 4, 5, 6. Minimum requirement is that you work with somebody else, period. All right? I don't care whether it's 2, 3, or 4 people. Just work with somebody. And I'm going to give you about 20 minutes here, let's say about 1:15-ish. I'd like for you to turn in a copy here, just one from your group that has everybody's name that works on it together. So, you can either work 2 and 2, or group of 3, or group of 4, I don't care. However you want to do it.
Do you want to order what? This week we're doing other groups. Oh, you're working with other groups? Yeah. No.
Anybody else have one to get me? Okay, as long as your name's on one, we're good. Let's pay attention here, folks. All right, here's your in-class worksheet. See how you did here. This particular one, is a limiting reactant problem. You would, if this was on an exam, identify this as a limiting reactant problem when the amounts of each reactant is given. Okay? So then what we do is we calculate multiple answers, and once you calculate the multiple answers, you pick out the answer that is the smallest. And why do we pick out the one that's the smallest?
Because we've run out of one reactant before.
Right, exactly. We run out of one reactant. So in this case, we're running out of the N2, which means we have H2 left over. Okay, then, next step on here was to calculate the percent yield if 52.6 kilograms of NH3 were to react. Well, remember now that this here is the theoretical yield. Percentages are always the part over the whole times 100, which is the same as actual over theoretical times 100. So you take the part, which was the 52.6, over the whole, which is the theoretical, the 59.8, you wind up with an 88.0% yield. The place where I saw the most questions was on the last one, which was what mass of which reactant remains unconsumed. And I saw multiple ways of solving this one out here, and those multiple ways, in most cases, were correct thoughts, didn't always result in the correct answer. But what mass of which reactant remains unconsumed? Now, if N2 is the limiting reactant, the one that's unconsumed is the hydrogen, or the H2. You know how much you started with, which is the 22.3 kilograms. If you know how much you started with, then you should be able to figure out how much was used or reacted. If you figured out how much was reacted, you could then subtract that amount from the 22.3 kilograms of H2 and arrive at your answer. And again, there's multiple ways of doing it. This is one way of doing it. If you know it went to completion, you would have the 49.2 kilograms of N2 that reacted. And you could then figure out how many kilograms of H2 reacted. You then take this result and subtract it from the 22.3 kilograms of hydrogen we started with and wind up with the 11.7 kilograms of H2. Any groups get all three answers correct or very close to correct? Okay. Good. Good. Okay. Now, if you didn't, and you leave here today and you want this stuff, where can you find these answers? D2L. D2L. Remember, I put all the notes on D2L, including all my horribly recorded lectures, which I never listen to because I can't stand listening to myself. But they're there if you want to listen to it and everything later on. So any questions? All right. Next here for today. You know, I didn't even use this word yet, and that's because chemists themselves don't even use this word much. Stoichiometry. But stoichiometry is what we've been doing, and it's way too much talking. So I can talk really loud, but I don't want to. Okay, so stoichiometry is what we're doing, and stoichiometry is when we look at mass and mole relationships in chemical reactions. And up to right now, we've used these types of conversions. We've used molar masses as conversions. We've used molar ratios as conversions. We've used Avogadro's number as conversions. And we've used chemical formula relationships. And by chemical formula relationships, what I mean is something like this. If we had something like 1 mole of H2O, we would say that 1 mole of H2O contains how many moles of hydrogen? Right. So this is what we mean by a chemical formula relationship. It's just basically, and how many moles of oxygen would it have been? 1, right. So that's what we mean by a chemical formula relationship. And then the last conversion that we're going to look at is coming up here, and that is the conversion called molarity. And so really, chapters 3 and 4 on this mole stuff can be boiled down to really 5 types of conversions. And that's all we've really introduced here. I mean, we talked about the concept of limiting reactants and everything, but in terms of conversions, we're really only talking about 5 different types of conversions. And with these 5 conversions, we can do pretty much any type of mole calculation that we're going to encounter in this course here. So it's just a matter of manipulating them correctly. So like when we saw here today with this one, what do we call this conversion right here? This is a molar mass. This one is a
Molar ratio.
molar ratio. This one was Avogadro's number. So you can see here we're just using those as conversions, and those again are really the only 5 types of conversions you need to know. So with molarity as a relationship, let's look at molarity here. We define molarity like this. We define molarity as being the moles of solute per liter of solution. Moles of solute per liter of solution. And I think we did this when we went through density. Mathematically, the word per means to divide. So that means if we wrote out a formula for molarity, molarity would equal moles of solute, then what? Over liters of solution. And if we want to break it down a little further, we can use the abbreviations that we're using in our text. Molarity is abbreviated with a capital M. Moles abbreviated with MOL, and liters with L. And of course now, just like we went through here today, we could, if we want, multiply each of these by 1/1000th, and a mole per liter is the same as a millimole per milliliter. And of course, milli would cancel out. Or we could also use it as a kilomole over kiloliters. Of course, we don't use kiloliters a whole lot in here, but we may wind up using millimoles and milliliters a whole lot. So it's the same unit because, again, milli over milli is going to cancel out, leaving us with moles per liter. So the units there are alike. Now I think in lab, I'm not teaching lab this semester, but you should have seen these on labels already. So if you saw something like 6 with a big M, HCl, how do we read this big M? If we had to just speak this in words. 6 molar. HCl is the way we read it. So it's read 6 molar HCl, or 6 molar hydrochloric acid. And what this means is that there are 6 moles of hydrochloric acid per liter of solution. And again, we don't read it as 6 molarity HCl, we read it as 6 molar HCl. So I think we have enough time here today. We're going to knock off the next couple questions in your packet. This will be on the next page in there. And we have this question right here. We'd like to know, what is the molarity of 500.0 milliliters of solution that contains 16.8 grams of sodium phosphate? So now as you read these problems, here's what you should be thinking. First of all, if we want to know what is the molarity, that means we want to wind up calculating something that has units of moles per liter. And specifically in this case, the moles of which stuff? Na3PO4. That's specifically what we want to wind up calculating. So think about that. That's what we're going to put out here in our units. That's what we're going to try to achieve in the calculation. Moles of Na3PO4 per liter. And whatever we can do to get over to those units, we do. So the best way then on this one is to look at the amounts that were given, the 16.8 grams and the 500 milliliters, and think about placing them into a calculation. Which one of these is most easily converted to moles?
Grams.
The grams. Which one is most easily converted to liters? The milliliters. So we then want to put them in a calculation like this. We'd put in the 16.8 grams of Na3PO4 for every 500.0 milliliters of the solution. And I'm just going to put SOL in to abbreviate solution, because this is really moles per liter of solution. Okay, so now if we start with this and we want to convert to this, it's just a matter now of converting the units. And we can start by either converting the numerator or the denominator. So let's start with the numerator. How do we convert grams over to moles? Molar mass. So again, remember, we have 5 types of conversions. That's pretty much it with these. So just ask yourself, which conversion do I need? So we want a molar mass. In the molar mass, we're going to put which units on the bottom? Grams of Na3PO4, and on the top?
Moles of Na3.
1 mole. Molar masses are always the grams per 1 mole. So let's go back to our periodic tables. Anybody happen to need a periodic table today? I have plenty. Never have too many periodic tables. Where are they? Let's get them out if you don't have them out. Anybody need one? Anybody else need one? Yep. All right. Three sodiums, 1 phosphorus, and 4 oxygen. So coming back here, we sum together those atomic masses. Oh, there we go, kind of screwed up the size a bit. What do we wind up with for the molar mass?
163.94.
163.94, does that sound right?
Yes.
Yeah.
Okay. Grams of Na3PO4 cancel out.
Yep.
Then we have liters that we need to get to. We're given milliliters. So how do we convert milliliters to liters?
1 liter is 1,000 liters.
1 liter is 1,000 milliliters. Where does the 1,000 go?
1,000 was on top.
On the top. So there's 1,000 milliliters for every 1 liter. Milliliters are going to cancel out.
Left just moles of liters.
So now we wind up with units of moles per liter. We'll take the 16.8, multiply it by 1,000, divide it by 500, and we'll divide it again by 163.94. How many significant figures should be in the answer? 3. So drawing this out to 0.205. And of course that's moles over liters, which means we would rewrite this as 0.205 M, which we call molar, Na3PO4. Any questions on this one here? Okay, the next one. Reads, what mass of magnesium nitrate is needed to prepare 250.0 milliliters of 0.700 molar magnesium nitrate? And then describe how this solution is prepared. So let's start with the first part. This is actually a 2-part question. Let's start with the first one. I'd like to know the mass. Mass is measured in which units? Grams, right? So now if we look at this, here's another key. We see two quantities separated by the word of. Mathematically, what do we do when we see two quantities separated by of? We multiply. Just like per means to divide, of means to multiply. See, you learn something new every day. Thank God for chemistry. All right, we take 250 milliliters of, which again means we're going to multiply. 0.700 molar Mg, and then NO3 parentheses 2. Of course, not a whole lot of fun stuff happens when we leave big M in there. Remember, what does big M stand for?
Moles per liters.
Moles per
Liters.
liter. So we're going to substitute in moles per liter. So again, remember, big M here stands for moles per liter. Well, we're still not quite in position to cancel out units, but then we should remember the relationship between milliliters and liters. How many milliliters are there? 1,000 milliliters for every 1 liter. So in other words, I have 1 liter written here. It'd just be simple for me to replace that 1 liter with 1,000 milliliters. And again, there's a million different ways you could do this one. Well, maybe not a million, but there's lots of different ways you could do this one. I like to do it this way. And why? Units cancel out, just like this. And again, that's because 1 liter is the same as 1,000 milliliters. Now, of course, we're trying to get to units of grams. So we want grams of magnesium nitrate out here for the answer. So at this point, what do we need to do for our units? This is going to be what type of conversion? Molar mass, right? And the molar masses are always the number of? Number of what? It's the number of grams for every 1 mole. Always. The number of grams for every 1 mole. So we go ahead and calculate the grams of magnesium nitrate in 1 mole of magnesium nitrate. So we'll go back to our periodic table. We have 1 magnesium, 2 nitrogens, and 6 oxygens. So 24.31. 31 plus 2 nitrogens plus 6 oxygens. Do you get 148.33? Yes, okay. So we put in the 148.33 here.
I have a question. This
Oh.
will be mole square. Multiply.
Oh, what am I doing wrong with this one?
We need to swap them.
Yeah.
Yeah, I'm putting it the wrong way. See, that's the beauty of dimensional analysis. You just try to cancel out units and figure out that it's not working too well, huh? That's why you're confused. I wasn't confused until I found out I was, right? See? That's why I don't listen to my recordings, because then I get really embarrassed. Okay? Now, moles of magnesium nitrate cancel out. And then we multiply through on here. We take 250, multiply that by 0.7, multiply again by 148.33, divide the result by 1,000. How many significant figures should there be? I hear 3, I hear 4, it is 3. Fewest of these here is 3. So this is going to be 26.0 grams of magnesium nitrate.
Magnesium nitrate.
Okay. 26.0 grams of magnesium nitrate. Okay, then the last step on this here was to describe how the solution be prepared. In other words, and you're going to be doing some of this stuff in lab. I don't know when because I'm not teaching it this semester, but I know you'll be doing some of this stuff. You use these devices right here, or you will be. You use these yet?
No.
No? Okay, what are these called?
Volumetric flasks.
Volumetric flasks. And these volumetric flasks measure 1 volume. And they come in all sorts of different sizes, but they got a little etched line on the neck that when you fill it up so the bottom of the meniscus is on that line, it measures that 1 volume. So in this case here, what size volumetric flask am I going to pick?
250.
I'm going to pick a 250. So again, this here is a volumetric flask, and I'm not, oh, that's not too bad. Kind of looks like a nose, all right. Okay, but this is my volumetric flask. And here's what we're going to do now. If I set you in the lab, what stuff are you going to measure out?
The magnesium nitrate.
How much magnesium nitrate?
6.0 grams.
All right, so what we're going to do is we're going to weigh out 26.0 grams of the magnesium nitrate and then place it into what?
Flask.
Which flask?
Volumetric.
How big a volumetric flask?
250 mil.
Right. So we're going to place it into a 250 milliliter volumetric flask. Then what?
And add water to dissolve.
Add water. Mix to dissolve. And then what we're going to do is we're going to fill to the line, fill with water to the line. And then mix thoroughly. And the reason why we do the water adding in 2 different steps is for this reason. And we'll probably go over by about 1 minute. I apologize. Okay, let's say that I was mixing together. I had a couple different beakers of sand and marbles. In one beaker I have 150 milliliters of sand. Another beaker I have 150 milliliters of marbles. I pour the 150 milliliters of sand into the 150 milliliters of marble. What volume am I going to get?
A little over 150 milliliters.
It's going to be over 150, but am I going to get 300 milliliters? No. Why not?
Because space.
Right, the sand fills up the space between the marbles. Now the same thing happens here. When we add water to the magnesium nitrate, you have crystal structures, and those crystal structures take up space. And the water is going to go in and fill in that space between them, and in the end, if you mix it together, you're not going to get the right amount. So you add in the water basically to fill up all the space, you then mix it up thoroughly, get it all to dissolve, then you add water to the line, since all the holes have then been filled in, and then you mix it up and you have your solution. And I like to call this the Kool-Aid rule. And I call it the Kool-Aid rule because if you've ever made Kool-Aid, it says you're going to make 2 quarts. It doesn't say you add in 2 quarts of water. You make a total of 2 quarts of solution. And probably the biggest mistake people make with these is to say to add 250 milliliters of water. If you add 250 milliliters of water, you're going to be making more than 250 milliliters of solution. All right, that's it for today, folks.